Welcome! In this lesson, we will build an intuitive picture of the Himalayas and the Tibetan Plateau. We will explore the collision between India and Eurasia, the modern deformation we see with GPS, the seismicity and the megathrust, uplift and erosion rates, and how the landscape records these processes. First, the big picture. The Himalaya-Tibet system is the type example of continent against continent collision. India moved north and collided with Asia about 50 to 55 million years ago, shortening the crust by roughly 2,500 kilometers and thickening it to build the high plateau. The Himalayan wedge in the south includes, from south to north, the sub-Himalaya, the lesser Himalaya, the greater Himalayan sequence, and the Tethyan Himalaya. These are separated by major faults: the main frontal thrust at the range front, the main boundary thrust, the main central thrust, and the South Tibetan detachment. At depth, a master detachment called the main Himalayan thrust connects them and dips beneath Tibet, doubling the crust to about 70 to 80 kilometers under southern Tibet. India continues to converge at about 40 to 50 millimeters per year, providing the energy that keeps this mountain belt active. Today, GPS shows that convergence continues at roughly 40 to 50 millimeters per year. About half of that, around 20 to 25 millimeters per year, shortens the crust across the Himalaya. The rest is spread across Tibet, where the plateau moves generally eastward, with strike-slip faults along the edges and even zones of extension inside the plateau. This eastward motion is often called continental escape. Normal faults within Tibet show that the high plateau is also stretching as it remains thick. The region is very seismic. The main Himalayan thrust is locked near the surface and has produced great earthquakes. In 2015, a magnitude 7.8 earthquake ruptured beneath Nepal. In 1950, a roughly magnitude 8.6 event struck the eastern Himalaya near Assam. Some segments farther west, and in Bhutan, look like seismic gaps. Geophysical imaging shows the cold Indian lithosphere dipping far beneath Tibet, helping double the crustal thickness. The Himalayas are still rising. Many areas uplift a few millimeters per year, with roughly 1 centimeter per year in the most active belts in the long term. Here is a simple comparison: Central Himalaya 1 to 3 millimeters per year, Kathmandu Valley 4 to 5 millimeters per year between earthquakes, and hotspots at the syntaxes like Nanga Parbat and Namche Barwa at 9 to 13 millimeters per year of exhumation. Meanwhile, parts of the frontal belt may be subsiding as India dives, and parts of southern Tibet are also rising a few millimeters per year. Erosion is intense, especially on the monsoon-facing southern side. Heavy rainfall drives rivers and landslides that can keep pace with uplift. On average, the humid eastern Himalaya erodes around 2.9 millimeters per year, while the drier western Himalaya erodes around 1.1 millimeters per year. Landsliding often controls how fast rock reaches rivers, coupling climate storms to tectonic relief. Rivers and valleys record uplift. Where uplift increases, channels steepen and form nick points. Faster uplift also narrows valley floors, carving deep V-shaped gorges. South of the range, the Indo-Gangetic Plain is a flexural foreland basin that stores eroded sediment. To summarize, the Himalaya-Tibet system is a collisional mountain belt built by ongoing India-Eurasia convergence. Half the convergence shortens the Himalaya, while Tibet moves eastward and even extends in places. The main Himalayan thrust produces great earthquakes, and geophysics shows Indian lithosphere underthrust far beneath Tibet. Uplift is rapid, up to about 1 centimeter per year locally, and erosion by rivers, landslides, and glaciers keeps pace in many areas. The landscape records uplift with steep channels, nick points, and narrow valleys, while the foreland basin stores the sediment. This active orogen remains a natural laboratory for understanding how tectonics and climate shape Earth's highest mountains.